My name is Paul Beaton, as Mario said, Senior Manager of Data and Analytics at Rogers Communications. And today I'm going to take you through using large language models for data imputation. As Rogers starts to look at different ways of how we can use AI, how we can really, use it in different and I don't know how else to say it, different ways for ourselves as opposed to a chatbot. I stumbled across this this study by Zhicheng and company, data imputation using large language model to accelerate recommender systems. And what they do here, what the team does, is they take a data set, a pretty common data set you guys have probably seen if the engineers and the analysts in the audience are familiar with Kaggle. It's the MovieLen data set used quite often. They take this data set, they have the rows of the data set that don't have any null values, they feed that into an LLM, in this case it's GPT-2. That pre-trains the LLM, and then they use the LLM to impute the missing data on the remaining rows of the data set. So after that, they have a fully imputed data set. They run that through a regression model. They have a recommender system. And they measure that recommender system. They measure it across RMSE, mean absolute error, mean square error. And then they also compare it against other imputation methods, as you can see here. All right, my laser pointer works. Case-wise deletion, if you're familiar with it, of course, just keeping those rows that have null values out of the equation, replacing null values with 0, replacing null values with the mean value of the variable. K-nearest neighbors classifier to impute the data, and a multivariate regression algorithm to impute this data. And as you can see, the LLM was the superior imputer here. That's great, right? Wow, we have LLMs doing, again, outperforming a lot of classical machine learning algorithms. The RMSE here, 0.9822, and lower mean absolute error, lower mean square error. So how did they come up with the missing rows? The MovieLen data set, if you're familiar with it, actually doesn't have any missing rows. It's a very clean and series of data that you can use in different ways. But they had to introduce null values into this, and they did this by basically randomly selecting 5% of the data points, completely at random, and then kind of artificially creating missing data that way, right? So I thought, in the data that I see every day, probably the data that you see every day, I see data sets with a heck of a lot more than 5% missing data. That would, actually be maybe a great data set to work with. So I wanted to replicate what they did across data sets with 5% missing data, 10% missing data, and 15% missing data, just to see, hey, does the LLM work as well when we have more higher levels of missingness, right? So just graphically, what that looks like, again, missing completely at random was the missingness that I introduced here. In the top left, 5% missing data. This is the data set right in front of you. A black square basically means there's a non-null value in there. A white square means there's a null value. And so you can start to see as you get into 10% and 15% missing data, a lot of white there, a lot of missing data. So my methodology, pretty much the exact same as Zhicheng and team. Do the exact same thing that they did in their study. Take the data set, run the non-null rows through an LLM. In this case, actually, the only difference being my LLM was actually GPT-4. That's the GPT model you get when you sign up for OpenAI's API. And then using that model to impute the missing values, feeding it into a regression model, creating a recommender system, doing that again for the 10% missing data set, doing that again for the 15% missing data set. Feature engineering, I didn't get any help, unfortunately, from Zhicheng. They left me to my own devices because they don't really say how they treat the data, how they create their regression algorithm. They just say that they use the user ID, movie ID, and genres field. So term frequency, inverse document frequency transformation on the genres variable because want to reduce a lot of the weight of some of the common genres. That's the data set. You'll see some genres are super common and then some very rare genres. It does a little better than one-hot encoding that way. Target encoding on user ID and movie ID variables, really just because of the high cardinality of these variables. In the full data set, there's something like 27,000 users and movies altogether. So I really needed to bring that down. Target encoding, as maybe some of you do know, is prone to overfitting, has a lot of data leakage in there. Because you're ultimately getting a category mean, you're stealing signal from that target to encode your variable. So I used a smoothing technique to basically create more shrinkage towards the global mean, less signal from the target, less prone to overfitting. And then 5-fold cross-validation and before a gradient boosted regressor on 150 trees. So maybe I cheated with the gradient boosted regressor, I don't know. Maybe they just use straight linear regression. But let's look at the results. Didn't quite hit Zhicheng and team's RMSE, I'm a few points off of that, but I think I have a workable model. And as you see for the 5% missing data, I replicate what he saw. I saw the same thing. The LLM, the superior imputer, outperforms zero switch or replacing null values with zero, replacing null values with the mean, KNN and regression. I didn't include case-wise deletion, and that's because the GPT, the imputer, or sorry, the LLM model that you get from OpenAI, the API that you plug into, it's very computationally expensive. I was using this on my own personal data sets before I pitched to Rogers, and we figure out if this is worth it. So I needed to kind of shrink the data set as much as possible because I only have so much of my own money out of my wallet that I want to put towards this, and time. It actually took about an hour and 40 to run through a data set of a couple thousand. But don't want to get too small because then you're likely to overfit with the gradient boosted regressor. So tried to walk the line there, and that's why you don't see case-wise deletion. But in any event, the LLM is superior. I want to show you, before we get into the 10% missing data set and the 15% missing data set, why I think the LLM was superior with 5% of missing data. And I apologize if that's small. Who has good eyes? Maybe I'll just read it out to you. The GPT response when you tell OpenAI, hey, fill in my data, this is what it spits out. It says, to predict these missing values, I'm going to analyze the data set, I'm going to find patterns and averages, and then here's my approach. So for this field, for the documentary field, all the values in the data set are zero. So I can fill this missing value with zero. I'm just going to, that's zero imputation. The drama variable, the average of the non-zero values is 0.558. So I'm going to use the average. I'm going to use mean imputation there. There's one in here that uses a mode, actually, where it says, I'm seeing a very common value of this amount, and looking like I'd probably use just the most common value in this case. So it's able to kind of reason between what's the best situation for imputing data here. And it uses some of the more simplistic methods, but says, oh, yeah, I'll use 0 here, or I'll use mean there. And that's what it comes to do. But 10% missing data, unfortunately, I wasn't seeing LLMs as the superior imputer anymore. It actually underperforms the 0 and the mean imputation methods that I saw as pretty simplistic and not as robust, maybe, in the 5% data set. 15% missing data, same story. It's just not the superior imputer. It loses out in both cases to a more advanced algorithm, k-nearest neighbors, and multivariate regression is what they use, and what I used. So not as good, right? That was an interesting finding. It led me to my conclusion that large language models, they appear less effective as imputation methods when your data set contains higher levels of missingness. At that 5% level, if there's around 5% or less, great, maybe this is doing better. But anything more, I was seeing a more advanced approach like the KNN classifier or multivariate regression to get a better recommender system. Tons of future considerations here, right? Like I think I really just scratched the surface. I did as little as possible to get in front of you guys here today. I just really wanted to come and speak. First off, the missing data mechanism, right? I introduced missing data completely at random. But I think probably, again, you've seen the data at your companies. A lot of the time, it's more likely going to be missing at random, missing not at random. It's going to be due to other variables in the data set or due to the variable or the value itself, right? You're probably going to see that a lot more often. Actually, maybe what I'm seeing, it looks like in data sets at my company, especially if it's survey data, right? Or something where we're just directly asking the customer, maybe a lot more black in each individual variable, but the one variable, will have tons of white because it's either a question that nobody wanted to answer in a survey, or it was a line item that's kind of not a lot of the population really fills out anyway. Maybe, if it's address data like a line 2, you won't see a lot there. So missing data mechanism, definitely want to play around with MAR, MNAR, play around at home, connect to my GitHub, connect with me after. I'll be happy to set you up. Small language models too. That was the other one that I just used this out of the box GPT imputer or GPT model. But as you work with the small language models in your own companies, the retrieval augmented generator is pointed towards your own internal company proprietary data. Does that outperform the out of the box GPT? Does it underperform that? And then I wanted to leave it as the last thing to talk about, because it's such a big thing in our field, prompt engineering for the GPT model itself. Further tuning of that, is that going to help us? Here's just maybe a snippet of my code. I pull in libraries, set my API key, and then create a function to impute with GPT. And I basically say, hey, GPT, you're a data analyst. Given this data set, predict the missing values and then return the missing fields filled in a Python dictionary so I can fit it back into a data frame there. But it's pretty vague, right? Like I'm just saying, hey, go on, impute, do your thing. Maybe if you be a lot more selective and you say, hey, in scenarios like this, you can use this type of imputation method. In scenarios like this, use this type of imputation method. This type of tuning to get a more superior result. However, as I'm seeing again, the missing completely at random, higher levels of missingness, LLM not the superior imputer. We're looking at more advanced algorithms, k-nearest neighbors, and multivariate regression as superior. So thank you for your time. Mario wants to say there are runners with the mic.
Yep, just raise your hand and somebody will come. So
yeah, in the back there, yeah.
Hi. Thanks for the presentation. So my question is, as far as I see, no offense or anything. So this is a published finding of another group, and you simply just reproduce the whole finding. So I'm just curious on like what is new here, and what are some additional insight that you can find that you can help enlighten the audience here. So for instance, like you mentioned about all those future direction, but have you given any consideration at all on what did you find, what is like different from the original findings, or are there any like practical challenge out there? Just some hints. I'm just wondering if you can share to us.
Yeah, no, that's great. And no, no offense taken, don't worry. Really the biggest insight is the level of missingness, right? That's what I wanted to experiment with. Higher levels of missingness, we're not seeing LLM to be as superior. So if you're, looking at using LLMs in your company to prepare data for your models, keep in mind the levels of missingness that you're going to use depending on what type of imputer you're going to use. And then I'd say, you asked about what type of drawbacks, I think you said, right? Like what things are really holding me back from doing this at Rogers right now. I mentioned it maybe only slightly. I didn't have a slide about it, but the computational expense and the financial expense of doing this was quite a bit. Now, obviously, I am doing it out of box. I'm using my own personal finances, so I don't have like an enterprise license or anything. But computationally expensive. Each row to impute that took quite a bit of time, and then it's quite a bit of money to do that. So if you are even better than I am, train a better model than I did, you're seeing the same types of things that Zhicheng and team saw, and you're only getting a smaller, tiny, insignificantly smaller lift in your model. How much did you actually spend on the LLM? How much did you actually use, again, computationally and financially to get to that stretch, right? So a big drawback, and thank you for calling that out, because I think I didn't call that out specifically, but my big insight is in terms of levels of missingness.
Gentleman here, please raise your hand. The runner will come for you. Yep.
Thank you very much for the presentation. So I think my question has to do with the conclusion that you drew from the experiment. Do you think it's a good conclusion? Like, can you draw that conclusion by carrying out an experiment on just one data set? If you say the LLM is not a superior imputer, you may want to try the experiment on multiple data sets across different domains, just to be sure that this is not as a result of the specific property of this data set. And if there are differences, maybe carry out some statistical significance tests to see if the result is different across like all domains, or it's just a fluke, right?
Yeah.
So if you don't conduct that, can we draw that kind of a conclusion? Like, can we say that the LLM is not a superior imputer?
That's a great question and a great comment. I mean, yeah, in terms of future considerations, I wanted to replicate what Zhicheng and team did as much as possible, right? To verify that and to kind of try and take the next step from what they did. But you bring up a great point. Is that data innately easier than what we're going to see in the wild? Can we do this exercise across different industries, across different types of data? As I mentioned, survey data has all types of missingness issues that you can see. Customer billing and information data, or like what's it called, geolocation data, has all types of a different type of missingness. So yeah, for sure. I think there's the other element to it is too. from what I saw in the study, I don't know how much Zhicheng and team really tried to make the best model possible, right? They have an RMSE of about 1. I don't think it's a super great fit. It's a workable model, right? I think I'd say that I'm fine with this for this purpose. But what about if you're getting into a much better fitting model? You really take the time to bring in as much data as possible, and you have a much better fitting model. Does LLM perform differently under that circumstance? You're absolutely right. That's a totally different area that you can look into. Yeah.
Thank you very much.
Okay, thank you. I see, yeah, the lady there.
Thank you. Thank you for the presentation. I'm wondering how effective is the prompt? I mean, I don't know whether the original paper provide the prompt or not, but did you try to write different prompts and does it change the, I don't know, maybe the order?
Yeah, that's again part of my future considerations. I didn't try different prompts, right? That's why I wanted to say, is prompt engineering going to be a big change if you do this yourself? The original paper did not have the types of prompts they use. They didn't outline that. Yeah, again, part of future considerations. I'm glad for all the questions, guys. That's like, hey, can we do more on this? I think you're right. I could have done way more. Please go ahead and research and do it yourself. I think it's an interesting way to use LLMs. It's not quite the same thing that I've seen a lot of people use them in this way. So yeah, if that answers your question, it is really just they had no specifics on what their prompt was, so I just used a basic prompt of, hey, impute this data for me.
Hi, just a quick question. Did you look at the different data types, like were numeric more effective in LLMs versus alphanumeric, et cetera?
Yeah. So again, the study wanted to replicate it as much as possible. Really only has the 3 independent variables: the user ID, the movie ID, and the genre. If you look on Kaggle, all the data sets that they have as part of the MovieLand data set, there's a few more things. There's a timestamp of when they when the person rated their movie. There is a relevance of their rating, depending on how much rating they typically give within that category of movie. I think those are typically the main pieces. The others are connectors. So there's a lot of other pieces of data in it. And actually in the study, they do compare that against not just regression, but a classification algorithm that I didn't do, that you could do for sure. I chose to go the regression route just because I wanted to zoom into it. I don't really have an answer as to why I did. It just looked interesting to me, so I wanted to drill into that. Yeah, but not as much, to answer your question, as I go off on another tangent. Not as much difference, I think, in the types of data you see in that data set. It's not a super wide data set in terms of the number of variables you're getting, personally, I thought.
Thank you. Any other questions? Okay.
Oh yeah, you guys.
Hi, thank you for the presentation.
Oh, thank you.
From what I understand, when it comes to imputation, it's important to understand the context of the variables used. So understanding of what user ID means. You think there is potential in tweaking the prompt in a way that you explain what each variable means and then have the LLM figure out? Because to me, it's right now seems like it's an over engineering done to a more simplified approaches of KNN, and where there's a meaningful way of imputing the missing value, as opposed to, because LLMs are trained on historical data, and historically these are standard methods, and to me it seems like most of the imputation it did was filling it with zeros, filling it with mode, and anybody would do that.
Yeah.
But is it like an over engineering unless you would tweak the prompt to explain what these are so that the LLM picks out a more appropriate approach for filling it.
Yeah, so if I can kind of maybe add to that, distill it and add to that, I'm kind of hearing you saying you can over-engineer it more. You can, as I was saying, you know, tell the ChatGPT to utilize these types of imputation methods based on a given scenario. I think I said, yeah, that would be, I think, a better way to approach. This is a pretty vague, just out of the box, GPT, go ahead and do it. But I think what you're also saying is, if you can kind of give GPT a bit of a background of what the data set is, what the exercise that you're doing is, what you're ultimately trying to accomplish here. You're trying to, you know, see what users will rate movies more highly and probably feed it into, you know, type of Netflix. You might also like this type of thing, right? So yeah, that's again a great suggestion. Yeah, I didn't think of that. Giving it the background so it kind of is not just saying, oh, okay, I'm an analyst, I'm just going to impute whatever, just do whatever I need to do to get a value out, but understanding the context a little bit more. Yeah, for sure. I think what was great about this is seeing that output, right? That's the output you don't really see in the paper. You see the output of the GPT imputation going line by line, row by row, and saying, here's what I'm doing, here's how I'm reasoning with it. So that was really cool to see, I think. So you're right. I think there's a lot of wiggle room in there for sure.